Let's review primary cells. The term battery refers to an arrangement of galvanic cells, or maybe just one cell, providing a source of direct current. Primary cells cannot be recharged. Once the reactants are consumed, the simple application of a current in the opposite direction will not regenerate the original reactants. Common primary cells are the zinc-carbon cell and the more reliable and longer-lasting alkaline cell. Secondary cells, which are the topic of this lesson, can be recharged. And I put recharged in quotation marks because there's a law of physics called the law of conservation of charge, which says that however much charge you have at one point, you still have that same amount of charge at some later time. In the case of a battery, sometimes that charge might not be where we want it to be, and we can put it back to where we want it to be by, quote, recharging, unquote, the battery. The original reactants can be regenerated by forcibly passing direct current in the opposite direction. We're going to go into detail here about the lead-acid battery or the lead storage battery. We're not going to talk too much about rechargeable AA batteries or rechargeable D batteries. And we want to talk about this one because it was the first rechargeable cell. It was invented, believe it or not, in 1859. That's not 1859 factorial, that's just 1859, which I find to be a little bit amazing. It was invented by this guy, Gaston Pontet, who was, a Frenchman. Lead-acid batteries are well known today for their use in motor vehicle batteries. Lead-acid batteries in cars consist of alternating plates of lead and lead dioxide. In my simple model here, we have alternating plates of lead and lead dioxide. Of course, an actual car battery is much more complicated than what I'm showing here, but I'm trying to simplify it, and then we'll see some pictures later on that are better representations of the actual structure of a car battery. These alternating plates are usually divided into 6 cells. The anode is the lead, the cathode is the lead dioxide. These lead plates are connected with each other. These lead dioxide or lead-4 oxide plates are also connected with each other, and we can imagine these little nubs that I've drawn here, this little blue one and this little red one, as being the terminals on the battery that you might have seen if you've ever opened up the hood of your car and looked at the battery. There are 2 terminals, and that's what I'm trying to represent here. Electrons depart the battery from the lead, because that's the anode, and they flow through the external circuit and re-enter at the lead-4 oxide. Electrons go from the negative battery terminal, which is usually blue or black in color, and flow into the positive terminal, which is almost always red in color. Now it turns out that physicists consider the direction of charge flow to be from positive to negative, when in reality what's flowing is electrons and they flow in the opposite direction, but that's not a topic that we want to get into. Each of these 6 separate cells, we mentioned that there were 6 of them, is bathed in sulfuric acid that has a concentration usually of between 4 and 5 molar. So it's pretty concentrated. Here's a better picture of a lead-acid car battery. You can see that here's a cell, and there are 6 of them in any given car battery. We've got the sulfuric acid bath that goes throughout the battery, and then we've got these alternating plates, and you can see that each cell actually has several lead plates and several lead-4 oxide plates instead of just the one that I showed on the previous slide. It turns out that each cell yields a potential of about 2 volts. So the battery, that is the 6 cells wired in series, yields a total potential of about 12. So a car battery is about a 12-volt battery. The oxidation and reduction half reactions are shown here. You can see that The lead is clearly being oxidized because it is losing electrons on the far right here. The lead 4 oxide is being reduced because it's gaining electrons. Let's kind of diagram what we're dealing with these equations. There are the two plates, right? You've got lead plates in the battery and you've got lead 4 oxide plates in the battery. Both of the reactions, the oxidation in the case of the lead and the reduction in the case of the lead 4 oxide, yield, among other things, this product, lead 2 sulfate, which is a solid. It is insoluble and it adheres to both plates. Those two electrons that are lost in the oxidation of the lead move through the external circuit and re-enter the battery to reduce the lead 4 oxide. If we add these two reactions together, you can see that the electrons will cancel on each side. We have 3 hydrogen ions on the reactant side and 1 on the product side. So when we add these, we've got lead 4 oxide, we have 2 bisulfate ions, we have a net of 2 hydrogen ions on the reactant side, and then on the product side we have 2 lead 2 sulfates and 2 waters. Now when a car is running, its alternator applies a potential in the opposite direction, which forces this reaction backwards. In other words, the alternator causes the lead 2 sulfate to be transformed back into the original lead and the original lead 4 oxide. We see that in the reverse reaction, lead 2 sulfate acts as a necessary reactant. The problem is that the lead 2 sulfate has to be on the lead and the lead 4 oxide plates in order to be affected by the alternator's oppositional potential. In other words, if for some reason that solid lead 2 sulfate breaks off and sloughs off the plate and sinks to the bottom, then it can't be part of the reaction anymore. So after many charge and discharge cycles and physical jarring from bumpy roads, some of the lead 2 sulfate breaks off and sinks to the bottom of the sulfuric acid bath. If that happens, the bisulfate concentration has to decrease. Check out the reaction at the top of the screen. If there is less lead 2 sulfate available, then can you see there must also be less bisulfate ion that is formed, that goes back into the solution. And if that concentration decreases, the battery can't be fully recharged. We can gauge the remaining useful life of a lead acid battery by measuring the density of the acid in each cell. In other words, you can see here, I'm circling on the left, whatever the bisulfate ion concentration is, if that is low, then the density of the acid is going to be lower than it should be. So it's actually fairly easy to gauge what kind of useful life we have left in our battery by simply measuring the density of the acid in each of the 6 cells.